honor indeed to chair a session here. Initially, I wondered, I am not an astrophysicist, as Samved pointed out. I'm a condensed matter physicist with superconductivity subject. There's a saying in Tamil which says, flies will be found in sweetmeat shop. What does a fly has to do in a blacksmith shop? Fortunately for me, the very first technical side, the opening talk by Professor Taut said that in the stars, the temperature and high pressure, electrons are degenerated and are superconducting. So he gave me legitimacy in chairing this session. So I thank him for that. Great. And I'm also very happy to chair this particular session where two of the speakers are former students of TAFR. I think the best reward for the efforts of Professor Chitre in establishing this center. Before I get to the session, am I audible?
Yes. Yes.
I just want to make one remark. Professor Srinivas Kulkarni, I believe, deliberately wanted to be a bit provocative. He seemed to be against speculation. I wish to state that science is exploring the unknown. Speculation is inevitable. Now, whether you wish to speculate or go to experimental science depends on your confidence in survival and success. So it's purely a matter of choice. I think people should speculate. Yes, of course, speculate with a bit more sense of responsibility or ensuring that you don't get into trouble. Now, let me start with the formal session. I am very happy to introduce Professor Saikia. He is a product of my own institution, TAFR, and he was a very lucky man to get his PhD from the father of Indian radio astronomy, Professor Govind Swarup. His career spanned in NCRA of Pune, and he has been working in the areas of exploring active galaxies, probing early universe through deep radio continuum surveys, neutral light absorption, etc. But the most important I note is the deep interest in science education, science higher education, the same manner which Professor Chitre devoted his later part of his life. So it's very, very appropriate that we have a talk from him. I invite now Professor Dhruva to present his talk.
Thank you very much, Professor Nagarajan. I'll share the screen again, I think. One sec. Slideshow. Okay, that's fine. Yeah. Okay, thank you very much, Professor Nagarajan. And let me first start by thanking CEBS for this very kind and generous invitation to speak on the occasion of the Chitre Memorial Symposium being organized by CEBS at Mumbai. Of course, Kumar I have known since I joined TIFR in the mid-70s, and he was extremely encouraging for me to join Govind in the radio astronomy group, a phrase which he used then, the sky is the limit, which he had used on many other occasions as well. And it was really a pleasure knowing him. And it was because of him that I taught a semester at CEBS, which was great fun. It was an opportunity to also, sit down in his modest office and chat on a number of occasions. So it was really great knowing him. And we were very lucky to actually grow up under the shadows of people like Govind, Kumar, Jayant, extraordinary persons with extraordinary vision. And yesterday, somebody also mentioned about Madhu Dandavati, and he was another extraordinary politician, a physicist. And I still remember, corresponding with him when as a youngster, I was worked up about issues. And as a member of parliament, he would actually write down replies on a postcard handwritten, which he had sent over. This is not the age when we meet such extraordinary persons. And hopefully, our next generation would be lucky as much as we have been. And today, in a symposium devoted to astrophysics and fluid dynamics, I thought I would pick on an area which covers both, because jets are basically relativistic fluid flows, And I'll touch on, because time is short, I'll touch on a theme, which is sort of recurrent jet activity in active galaxies. I'll be sort of biased and restricted in the sense that I will cover more of what we have done, more of what the GMRT has produced, and although I will allude to other studies as well. So let me start off. So the recognition of linear features actually goes back to 1918, more than 100 years ago, when Curtis recognized this wisp-like feature in this giant elliptical galaxy located in the Virgo cluster. He called it a curious straight ray, apparently connected with a nucleus by the thin line of matter. But the word jet didn't come into use at all. It was not thought about at that point of time, and it was left at that. It was nearly 36 years later that Bard and Minkowski, when they took a spectrum, first used the term jet because they saw blue shifted the oxygen forbidden transition at 3727 angstroms, and speculated that some of this emission must be coming very close from the nucleus and is probably part of the jet. So this was probably one of the very early, or perhaps the first use of the word jet in astrophysics. And it was later when Martin Schmidt recognized the redshift of the quasar, the first quasar 3C273, there was also an optical wisp, and he used the term jet to describe this as well. So jets, these were the early sort of forays into relativistic or outflows from active galaxies. It is perhaps fair to say that although some of the early 5-kilometer Cambridge radio maps showed evidence of jets, the ubiquitousness of how common it is connecting the outer lobes of emission to the nucleus of the active galaxy became apparent with the advent of the VLA late 70s, early 80s, which culminated in a seminal review by Alan Bridle and Rick Perley on radio jets in 1984 in the Annual Reviews of Astronomy and Astrophysics. Since this is a more general audience, I thought I would just spend a few minutes giving an introduction to the structures of radio galaxies, and then I will move on to recurrent jet activity and what it might tell us and why it is important. Now, as I just mentioned, that radio galaxies and quasars, the structures can be broadly divided. The outer two lobes can be broadly divided into two classes, which was done by Bernie Fanaroff, who was instrumental in getting this square kilometer ray into South Africa. This was while he was a student to Julia Riley, and realized that there were two kinds of sources. These are more recent maps. One, the class 1 sources, which had very diffuse outer lobes of emission with very dissipative jets, and often quite symmetric, at least on the larger scales. And the others were the class 2 sources, where the jets are very narrow and collimated, weak, not very dissipative, and ending in bright regions of emission, which are identified with the regions where this relativistic flow interacts with the external medium, forming a shock front, and this is where the energy is randomized and dissipated. So these were the two broad categories that they identified. The Fanaroff-Riley class 2 sources are more luminous. They're believed to have high Mach numbers, whereas these are lower luminosity objects, and the jets are believed to have lower Mach numbers. Sorry, I went the other way around. Yeah. Now, these radio sources actually can grow into very large sizes, over several megaparsecs in size. 1 parsec, for those who are not used to astronomy jargon, is 3.26 light years. So this is one of the, this is still the largest giant radio galaxy, which was found from a combination of observations with the GMRT, the Effelsberg telescope, and the VLA, which we found nearly a decade ago, and this still more than a decade ago, and this still continues to be the largest giant radio galaxy. Pratik Dabade, who is currently a research scholar about to finish his thesis at IUCAA, he has compiled an extensive list today, which is about 800 giant radio sources or so, presently defined to be anything greater than about 700 kiloparsecs. And this is another interesting source which you found, which you're working on. And this is just to show that these are cases where there seems to be continuous outflow of relativistic plasma from the active nucleus. The origin is believed to be accretion of matter onto the central black hole, which has an accretion disk around it. And although the detailed processes of jet production are not very clear. You can see that this has a kink, which perhaps is possibly due to precession of the jet, which is would be related to the precession of the black hole itself. Now, these are sources where you can see that the jet is continuous for time scales or quasi-continuous for time scales of about 10 to the power of 8 years or so, if you put in typical sizes and the velocities at which the hotspots are believed to be moving out. To reach these large sizes, they have to start off small. And these are just a collage of objects, which I told you about megaparsec scale sources. These are on the scale of parsecs to a few kiloparsecs or so. So these sources start off young. They have a bumpy ride, interacting with clouds of gas in the interstellar medium of the host galaxy as they propagate outwards. Not all of them perhaps do. Some may get disrupted, and some may be just transient events and not develop into the large sources that we talked about today. So radio sources are born due to accretion of matter onto a supermassive black hole. They grow in size from parsec scales to megaparsec scales. And they're broadly classified into the Van Ryle class 1 and class 2, depending on the structures. Optically, if you look at the spectra, they can also be classified based on the strength of the excitation of the emission lines over there. I'll not spend too much time, but just introduce the theme that there could be low excitation emission lines, high excitation emission lines. And this is a plot. There are better plots by Bess and Heckman. This is, I could easily pick up from a piece of work I did with Yogesh Chandola and Lee. And this just plots the O3 equivalent width versus the excitation index. So you can see the high excitation lines over here have large equivalent widths and a high excitation index as well. So the low excitation radio galaxies tend to be associated with the low luminosity Van Ryle class 1s, and the high excitation radio galaxies tend to be associated with the Van Ryle class 2s. Now, as the sources grow, the spectrum of these sources, they're non-thermal emission with a steep spectrum, but the most compact sources tend to get absorbed, and the low excitation, the high excitation radio galaxies follow perhaps different evolutionary trajectories from the most compact to the sort of small to the large. And this is broadly consistent with the observations that this absorption is largely due to synchrotron self-absorption, although in many cases, when they're buried right in the nuclear regions of active galaxies, free absorption by the thermal gas could also play a significant role. We had recently reviewed the properties of these compact sources for somebody who may be more interested. The velocities of these objects as they stir out and even at larger distances are typically of the order of 0.1 to 0.2 C, and the youngest sources can be hundreds of years old, whereas the largest sources are millions of years old, 100 million years old or so. Now we look at, as the source ages, what might it look like, and then we will move on to the recurrent activity or evidences of recurrent activity, which is important for a number of reasons in terms of understanding the effects of an AGN on the host galaxy. What would be effect if there is recurrent activity on different time scales on the star formation and the evolutionary history of the galaxy itself. A very old giant radio galaxy might look somewhat like this, where the hotspots are faded, there's no longer any energy supply. And as the electrons age, the higher energy electrons lose energy faster. So it steepens at higher frequencies, and the break or the region where it curves down shifts to lower and lower frequencies as the source ages. So there are caveats to this, but I'll not get into those details, but the ballpark number should be okay. So this one we estimated to be a spectral age of about 150 million years. You can also do estimates of ages from dynamical estimates of propagation of jets through the medium. So these were sources where we saw that the energy had either stopped or it was continuous over the lifetime of the radio source, which can extend to several megaparsec. Here is an example of a source where the energy has probably switched off. You have diffuse outer lobes of emission, and then it has restarted. So one would like to understand what are the timescales of episodic activity, what are the theoretical ideas behind it, and will it give us some clues towards understanding radio loud and radio quiet dichotomy as well? Because if you take a large sample of elliptical galaxies, only 10% of them are such luminous radio galaxies. I'll show you a few cases of where this phenomena occurs in a variety of situations. And this is the same source where if you look at the spectra of the younger source, you don't find any evidence of aging at all. It's a straight source, and the fifth given age of about 2 million years. We also did some dynamical age estimates, which gives a similar ballpark number. Whereas when you look at the extended lobes, which are the earlier generation of emission from the nucleus, you can see that it ranges from about 50 to 150 million years, depending on the assumptions which you make. So these can occur in a variety of situations, and the inner doubles can also take a variety of shapes depending upon variety of sizes, depending on the time scales. The other one was more than 100 kiloparsec, and here we have a small double, a mini double, which you'd only pick up if you looked at with observations of a few milliarc second or so, just 20 parsecs across, whereas the large scale diffuse lobes are about 1200 kiloparsec or 1.2 megaparsec in size. Yesterday, Anand Hota, this is an object we worked on together, showed you evidence of a source with 3 cycles of activity. And it's a very interesting object because it is also associated with a spiral galaxy. There are only very few examples of such cases. Most luminous radio galaxies are associated with elliptical galaxies. Now, I've showed you cases of Vanneroff-Reilly class 2 sources where there are where the 2 hotspots can be easily delineated, and you can find out evidence of 2 cycles of activity. What do you do when you get only FR1 kind of objects? This is one sort of object called Hercules A, where you can actually see evidences of the bubbles of plasma that are flowing out. But one is not always that lucky. One can try to find out by looking at sharp gradients in spectral index, because the newer plasma would be younger, as we just saw, and have a straight spectrum. Whereas the older plasma would have a steep spectrum, and you would see a sort of discontinuity in the spectral index distributions. This has also been seen in this object by Nectaria, Kitsani, and Paddy Leahy. Or you can make very deep images and try to pick out deep emission, which are more easily visible at lower frequencies. This is from LOFAR. When I first observed this source, I just picked up the central region and had no clue that there would be extended emission on a much, much larger scale than what we had been able to pick up many years ago. It is completely depolarized. There's no polarized emission from it due to the thermal plasma which exists in the central region of this source. So to push the ideas of or the time scales over which this can occur, Sumananandi and I and the collaborators, we have been trying to get more interesting objects and also push it down to smaller and smaller sources to see at what smaller scales can we see evidences of recurrent jet activity. Here I've just given you 2 examples that is also associated with a quasar. This is a red quasar, but it is a giant radio quasar. This is slightly smaller, but it's an elliptical galaxy where you see 2 cycles of activity, and this probably is located in a binary black hole as well. And from the radio structure, also you can see evidences of precession of the jet, probably due to the binary black hole system, one of which is giving rise to radio emission. When you go to the smallest of objects, the compact steep spectrum sources, which I talked about earlier, can we find evidence of emission in these objects as well? And here it is quite a challenge because you have to make a very long baseline interferometric observations where the number of antennas one can normally use is somewhat limited. You have to make high dynamic range images because you want to pick out very diffuse low brightness emission over here. This is a source OQ208, which was observed by Wu et al. And the Chinese collaborators, Chinese-American collaborators. And what you can see over here, images on the top is a tapered image, which is at low resolution, and the lower one is at high resolution. Different degrees of taper. And when you do that with low resolution, you can pick up the more diffuse scales of emission. And when you observe it at high resolution, you can see that this itself is a very beautiful double lobe with multiple hotspots and a jet-like structure over here. So here you have linear size of the double to be only about 10 parsec and relic emission, which is located about 40 parsecs away. So do these central engines keep sputtering, giving out such lobes of emission? And how frequently do they happen? We know several such cases, but how ubiquitous it is, we do not know, because this is something which we need to observe a much larger sample of sources to be able to get a good handle on that than what we have been able to do. But there are several other cases as well. And what I should also point out over here is that from these compact sources, as I mentioned earlier, because they have compact hotspots, you can do a lot of physics in terms of trying to estimate the velocities of advancement, how the jet interacts with the surrounding medium. So far, I've just talked about radio sources, but I'll just briefly also mention that these are aspects which you can also is also probe from observations at other wavelengths. For example, star formation, etc. You could look at it in the ultraviolet, do these jets trigger star formation, etc. But here's an example, a couple of examples I will just pick up to show you, just to illustrate the importance of also X-ray observations. This is an object which was picked up by Andy Fabian and his collaborators, and which shows this is an X-ray image from the Chandra deep field north, and overlaps with the Hubble deep field 130. And what we picked up was extended lobes of emission, a giant radio galaxy almost. Each lobe is about 345 kiloparsecs long, associated with the galaxy at a redshift of 1.99, which corresponds to a luminosity distance of 15.7 gigaparsec or so. Now, these X-ray emissions could have been generated by inverse Compton scattering of the low energy electrons, because the source is so old, you may not be able to pick up at radio wavelengths easily, but if it is inverse Compton scattered with a cosmic microwave background, you could pick up such old signs of emission from X-ray observations as well. Along with Catherine Blundell and a student, we made a deep observation with the GMRT. This was in the prior to the UGMRT days, and we did not see anything over there. Actually, we picked up a lot of other sources, but maybe it's time to make another deep image with UGMRT and see if we can pick up an old relic from here. There are other examples as well. The famous source Sigma Se, which many of you would be familiar with, that there is a counterjet which seen in the X-ray, which does not quite coincide with the radio in all its ways. It deviates from it. And this counterjet could also be a previous cycle of radio emission, which has been inverse Compton scattered to X-ray wavelengths. So X-rays also provide us a means of trying to probe very old electrons via inverse Compton scattering. The other way of actually looking at cycles of activity is to look at the cavities which are formed in clusters of galaxies. This is the famous source 3C84 in the Perseus cluster. Superimpose other radio contours on the X-ray image, and you can see the X-ray cavities created by interaction of the radio plasma with the X-ray emitting gas. I picked up this image to illustrate, although it is not very clear in the image and is often a challenge to pick it up, because in addition to the large cavities, there are two smaller cavities of about 20 kiloparsec along the jet axis. Vantigam et al. Have made a very detailed study of this source, and for cavities with multiple cycles of activity, they plotted the outburst intervals, which you can see ranges from, of the order of, in the errors, 10 to the power of 6, is it? 10 to the power of 6, sorry for this error over here, to about 10 to the power of 8 years or so. So you can see there are evidences of multiple cycles of activity from radio and X-ray observations. And today we are in an era where we are getting low frequency telescopes, whether it be LOFAR, GMRT, or the upcoming ones such as SK, which will come up, that we will be able to probe much more of this. With the MWA, the Australian telescope operating at low frequencies, they have picked up cases where you see evidence of a compact source, and then there is extended emission, which would be optically thin at low frequencies. And these are telltale signs, but we still have to try and confirm from actual images that this is indeed the case, and there is not something confusing within the beam, but these are promising candidates of sources. Many years ago, using interplanetary scintillation observations at UT, Jay Kumar at that time also, we tried to find evidences of it by looking at the scintillating flux, which would be the compact one, and comparing with the large-scale flux, and we found several cases where there would be evidence of large-scale emission. But we didn't have good maps to confirm it, and today is the era when with LOFAR, UGMRT, etc., that we are in this very privileged place, privileged time to probe this much further. The various theoretical models which have been ideas which have been put forward in the early days when these were only seen by the pioneering efforts of Arno Schoenmakers, although cases were known before him, but he made a systematic study, that these are all known in giant radio galaxies. And Kaiser et al. Asked the question that from the earlier cycle of activity material has been swept out, how do hotspots form in the second cycle of activity? And they said that perhaps in dispersion of intergalactic medium clouds into the cocoon, which would take a time scale of about 10 to the power of 7 years, facilitates that. As we pushed our cases of recurrent activity to smaller and smaller sources, we realized that this could not be applicable in all cases. I will not discuss every paper in detail, but I think the question of what triggers this multiple activity is something which sort of challenges us, because it is intimately related to the question as to what triggers the radio source itself. Reynolds and Mitch-Begelman, they looked at the evolutionary timescale, the evolutionary scenarios of sources, if emission was intermittent on timescales of 10 to the power of 4 to 10 to the power of 5 years. Shavala et al. Said the radio sources in the most massive galaxies are retriggered more frequently. Kuzmix et al. Compiled a sample of over 70 sources and compared it to ordinary FR2s. Something so similar like black hole masses. There were differences in concentration indices, which could be due to mergers of recent companions, but results have been questioned. So I think we need to do more systematic work with larger samples. Chitre, my former student, has been looking at environments of these sources from X-ray observations. So there are a whole lot of questions, areas, looking at it from different aspects.
Saikia, you have about 5 minutes.
Yeah, I will finish off in a couple of minutes. I'm timing myself.
Let's take a few more minutes. It's okay. Error bar is 5 minutes.
Yeah, sure. And so the question we were trying to ask ourselves is that if, for example, these cycles of activity are triggered by accretion of matter into the central black hole, either in the Van Allen-Rayleigh, two cases, it is believed to be minor mergers of galaxies, perhaps a dwarf galaxy which has been swallowed up. Whereas in the FR1 kind of galaxies, as I mentioned, the evolutionary scenarios could be different. It could be hot gas, which is cooling and accreting onto the central massive black hole. And what we tried to do was try to ask ourselves, can we find evidence of this gas more frequently than in other cases? And what we did was we tried, for wherever possible, we tried to follow it up. We tried to look at it with GMRT and Arecibo telescope. Can we detect H1 in this absorption in these cases? What are the kind of profiles? Do they tell us anything? And today we have looked at not too many cases, but a number of cases, and almost every case that we have looked at, we have found H1 absorption with very complex profiles. And if we look at the incidence of absorption, we have been doing surveys of other complex sources plus larger sources as well, that the incidence of absorption in these rejuvenated sources is almost 100% right now, but is obviously based on small samples, strong selection effects, because only we can do it for the stronger cores to be able to detect it. If the cores are weak, we cannot see it. These are examples of 4C29.30, an FR1 kind of structure. On the outer side, diffuse lobes, but inner you can see prominent hotspots where you see absorption to the core. And these profiles are also often very complex, showing that there are various H1 absorbing clouds at different velocities. This is one case which we sort of observed with the Arecibo telescope, which sadly is no longer there. A very compact source, I showed you larger sources over there, which is only about 15 milliarc seconds in this case. And I've given the scale of what 1 milliarc second corresponds to. And you can see large scale diffuse emission, which is picked up by Daniel Dalla Casa with the European VLBI network of lower resolution and lower frequency. And you can see a very prominent absorption line, which was detected for the first time with the Arecibo telescope by Chris, me, Robert Minchin, and Yogesh put together. So there is evidence of gas. Lakshmi looked for it in carbon monoxide, but carbon monoxide has not been as successful. This should be a J, I'm sorry about this typo, has not been as successful. I think we probably need to hit these hard with ALMA to try and see the H1 gas in them. So high incidence of H1 gas in rejuvenated sources shows that there is recent accretion of gas. A sample is small, as I mentioned earlier, and also we have been able to do it only for sources with strong cores. In terms of the variety of phenomena of a variety of cases, which you see rejuvenated activity. I've shown you a few examples. I'm sure with new images coming out from LOFAR, UGMRT, ASCAP, MeerKAT, JVLA, and in future SK, we will probably pick up much more and probably a much wider diversity as well of trying to identify recurrent activity in electrogalactic nuclei. And as I mentioned, this is important not only to understand the physics of evolution of radio galaxies, but the evolution of the galaxies themselves, and in clusters, the evolution of clusters themselves, because these are what are inputting energy into the interstellar medium of the host galaxies and affecting their evolution, or the cluster environment and affecting the clusters of galaxies as well. But the fundamental question still remains, that what triggers nuclear activity. And to my mind, this is still an open question. Is it a combination of mass, spin, magnetic field, which can channelize the plasma that is generated, accretion onto the disk? And this is something which I hope that we will get much clearer answers as we go along, and that recurrent activities or studies of these galaxies may give us some very useful insights. Thank you very much.
Yeah, for your very timely, time-restricted talk. I admire you for timing your talk so well. We'll take 3 questions. Let me see if I can see the chat box. I will just get it. Got into something else. Just 1 minute, please. Sanskriti, you had a question. Can you ask that?
I just wanted to ask, are these jets also observed in spiral galaxies?
Actually, the thing is that spiral galaxies, generally you see jets in them, particularly the subset of spiral galaxies called Seyfert galaxies, which is also a low luminosity class of AGN, but they are less luminous than that of the radio galaxies which I showed you earlier. But amongst the luminous radio galaxies, there is a very small number which are associated with spiral galaxies. The object which Anand Hota showed yesterday and I showed today as well is associated with a spiral galaxy. But there are just a handful of them. The bulk of the very luminous radio sources, which should mean greater than about 10 to the power of 25 watts per hertz per steradian at a few hundred megahertz, they are largely associated with elliptical galaxies. The spiral galaxies have jets, but of lower luminosity. In fact, in a recent study which we had done led by Raniero Baldi, and which we started while I was at Jodrell many years ago, that we find jet-like structures even in galaxies which are referred to as H2 region galaxies, which are dominated by just star formation, that you can make out collimated structures right in the central region in some of them. So the answer is yes, spiral galaxies have very collimated structures. NGC 4151, NGC 1068, Markarian 3, Markarian 6. These are sort of archetypal examples of jets in spiral galaxies.
Thank you, sir. I have a question from another of our student, Chandrasekhar Iyer. What are some characteristics different that we observe between objects with low redshift and high redshift?
Okay, there is, okay, let me just give you 1 or 2 examples, okay? One based on what I have spoken about, one based on something I've not spoken about today. For example, if I look at galaxies themselves, the way they look, if you look, I mean, one ends up when one does introductory astronomy and astrophysics, one of the first things one learns is Hubble's classification of galaxies. And you see the beautiful elliptical galaxies, you see the beautiful spiral galaxies. Hubble concentrated largely on the nearby beautiful sort of spirals, ellipticals, and he classified them. But when you go to higher redshifts, you find that the situation is far more complex. There is far more interactions between galaxies. The Hubble fields actually show a wide variety of galaxies. And some of them have very complex structures, signs of interaction, some look like a tadpole, some look like a mess, but there is a whole variety of galaxies which show much more interactions. Not that interactions are not present in the nearby galaxies, they are, but the kind of structure, but they're much more prevalent in the early ages of the universe. For example, Somak usually talks, who might talk about clusters of galaxies a little bit, will tell you about the kind of complex structures that you see when galaxies interact with one another. That is one sort of very broad difference in terms of the morphological classification of galaxies. But if I look at radio sources themselves, evidences are that the linear sizes of radio sources were smaller at earlier epochs, probably due to a combination of higher density. Also, probably large diffuse sources would be snuffed out by inverse Compton scattering with the cosmic microwave background. Some of them we may be able to pick up at X-ray wavelengths. In fact, when I look at the large giant radio galaxies, there are very few of them beyond a redshift of 2. And this is perhaps due to the effect of both density and the cosmic microwave background. So there are distinct differences in terms of the evolutionary properties of galaxies themselves, luminosity evolution, density evolution, morphological classification, structures of sources. So there are a lot of differences. I mean, I would be happy to sort of, as a student, if you email me, sort of engage with you more on this, but this is just a very, very brief summary of your question.
Thank you, sir, taking pains to explain to our students. There are two more questions. I will take one of them. I request Sankalp to discuss with his question later. The first question directly related to jet property. The question is, do we find difference in recurrent jet properties between FR1 and FR2? Since FR2 are lossy jets, hence brighter, it may have dense environment. So kindly comment on it.
Yeah, actually, sorry, thank you very much. In terms of FR2 recurrent activity, I showed you Hercules A, and there is a metal lobe in Centaurus A. There are very few cases which we know of, and that is because of the difficulty in trying to identify clearly, because in an FR2 source, you can see the hotspots very clearly. And so you can say, hey, you know, you see an edge brightened structure. If you map it in polarization, you see the polarization structure. You should see the polarization structure, which you see at the end of a hotspot. So it is much more easy to actually pick up the FR2 sources with multiple structures. But when in FR1 sources, where they diffuse into each other, the whole jet, that it is not as easy as in the FR2 cases. So right now, the number of FR1 clear cases with recurrent activity are rather small in number to actually sort of talk about differences between FR2 and FR1s, but hopefully with new data, I mean, LOFAR is just releasing releasing their new data set over a much larger area of the sky to a lower flux density limit. And these are issues, I think, which we will, or we should be able to take up and answer more satisfactorily. Right now, I think to answer your question, the numbers are too few, and I would probably not hazard a guess right now. Thank you very much. Yeah.
Thank you very much, sir. Now, can we move on to the next speaker, please?
Okay, I'll just stop sharing. Yeah?
Right, shall I share my screen?
Okay. Welcome, Somak. Let me introduce in a very brief way. He is an important person in Indian astronomy because he links the universities, as he is the director of Inter-University Center for Astronomy and Astrophysics at Pune. In the tradition of Professor Chitre, he got his PhD from Cambridge. Getting a PhD from Cambridge is a very that itself is a unique award, but he has got other awards as well as early career, Smith Prize, and Isaac Newton Prudential. So he is obviously an eminent academician. His areas of research are gravitational lensing, galaxy dynamics, and large-scale motion in the universe. I fondly remember Professor Chitre giving me a perspex piece shaped like a gravitational lens. I'm only sad that I misplaced it somewhere. I hope I locate it somewhere. Thank you, sir. Please present your talk.
Thank you very much. I hope you can see the screen.
Yes, we can.
Yeah, I chose this topic because, of course, this is something in which Professor Chitre and I discussed quite a lot. I first met Professor Chitre, I think in 1982 when I was a visiting undergraduate student in TIFR. But I really got to talk to him in Cambridge when I was a PhD student in Churchill College. He was also a visiting fellow in Churchill College and used to come every summer. And in '86, he was spending almost half a year there with his family, along with Charles Gurria, actually, at the same time. And at that time, I started talking to him meaningfully, almost every day, on various astronomical topics. And he was very interested in gravitational lensing at that time. And we got talking about quite a lot. And that actually eventually got me into gravitational lensing. And later I met, of course, Narasimha, who's already given, Dr. Narasimha given a wonderful talk on gravitational lensing the first evening, and the 40 years of work that he's done with Professor Chitre. And one of the things that during the dinner times in Churchill College, and also, but later on, I must say that one of the things that I have to say about Professor Chitre is that he always looked after younger colleagues, no hierarchy in mind, very simple and very, very honest person. But and in my life, he's had a very, very huge impact because almost every decision I've taken in life, including coming back to India and coming to IUCAA, all of that I discussed with Professor Chitre, and he gave me his amazing, valuable advice. So, but in those early days, 35 years ago in Churchill College, as Dr. Nagarajan just said, he had built all these models, Perspex models, as you know, in TIFR, which I first saw when I visited as a student, and was amazed. And during the time in Cambridge, he used to show how, to my horror, one day he broke a wine glass, and the fact that the base of the wine glass has the variable thickness that could act as a gravitational lens was amazing. I mean, he just demonstrated that, and a lot of people later on have done this. This is from Phil Marshall's web page, for example, that if you build these models in with Perspex or glass, you can actually simulate a gravitational lens. So that's wonderful innovation that Professor Chitre, his colleagues would remember. Just talking about, today I want to talk about groups and clusters of galaxies and how the interesting link with gravitational lenses. As you know, this is a simulation, of course, of dark matter in the universe, and matter is clumped into small into clusters, which are the crossings of the filaments of the cosmic web. But actually, most galaxies live in these small systems, very small dark matter halos, which would be called groups. And they can, in galaxies, they're very hard to see because they're dark matter clumps, but they accumulate a lot of gas, and this gas then gets thermally heated up, and they emit X-rays due to thermal Bremsstrahlung. And if you look at X-ray images of galaxies, and then in galaxies you also find hot gas, X-ray gas, but that's a tracer, don't have much. But as you go up the mass scale, you can find groups and clusters of galaxies where actually the hot gas plays a very important role in the mass fraction. It's a very important part of the baryonic mass fraction of the group. And so groups are these intermediate kind of structures of galaxies, which are hard to detect, very hard to detect if you're just looking at optical ranges. But then they're important because most galaxies live in small groups. Here is a very good, very complicated plot, but I'd like you to look at this left plot, which is essentially a histogram of from a large survey. This is from the 2DF survey of galaxies, in which you study the aggregates of galaxies. Galaxies don't like to live alone; they live in little groups and clusters. But if you look at the mass distribution of such systems, you would find then the x-axis is the log of the light. So this tells you what the size or scale of the aggregate is, and the histogram peaks at around something that has the light of 10 to the power 10.5 or 11, which corresponds to something like 10 to the power 12, 12 and a half in solar masses, and so that's like a group in which there are 2 or 3 major galaxies. And that's where most of the galaxies live. The rich clusters are right at the end here, and essentially about 2%, 3% of the stars are found in rich clusters. So if you want to understand galaxy groups, if you want to understand galaxies, how galaxies evolve, they evolve mostly in very small systems, and these are very difficult to detect. And groups are also very interesting because they come in a diverse bunch. There are groups that are very nice and symmetric. These are all optical images on which X-ray images have been superposed. But then you can see something that looks like a scrambled egg and stuff like that. So essentially, groups have very different morphologies because they are all galaxies coming together, forming systems. And when you look at clusters of galaxies, they are very nicely formed systems already. Now here are good examples of clusters of galaxies, famous clusters of galaxies at various redshifts. These are high redshifts, Z of 0.4, 0.6, and stuff like that. These are out to very large distances, but you can see these clusters very clearly because there are hundreds of galaxies, hundreds of big galaxies in these systems, and they're very bright, and you can see them, and consequently for years, people have studied these systems. But as I said, most galaxies are not in these clusters. And so they are very, and so if you study only clusters, you get only biased view. In fact, galaxies at the end of their evolution end up these systems. And so you don't really get to know about the teenage years of the galaxies, when galaxies are forming and galaxies are evolving. So, so these systems are hard to detect. So, for example, here are pictures of from the Gamma survey, and these are near-infrared images from WISE of groups of galaxies found, the farthest groups of galaxies, really. So here are clusters at redshift of 0.4, and you can clearly see them in HST images. You take a small group of galaxies in which most galaxies are, and to image them is very, very difficult. You can't really find them, and you can see that you can barely see the group in these systems, and these are at redshift of 0.1, right, and 0.05. And only very nearby systems, which are at 0.02 or something like that, very, very nearby, 100 megaparsecs, something like that, you can see them. Because these are not high over densities over the background. So this is one motivation of my talk today. How, if you want to study galaxy evolution, you know that they're in very small systems. You have to find ways of detecting them at high redshift. Otherwise, you don't see, because the higher redshift you go, the earlier in the age of the universe you're going. So if you want to see galaxy evolution, you have to pick up the early times for galaxies, and then you cannot really find these groups at very large distances. So what is a good way of finding them? As I said, one good way of finding them is to take X-ray images, deep X-ray images, and the X-ray images actually trace the hot gas, not the galaxies, because the galaxies, there are 2 or 3 galaxies in a group, and you won't see them, you won't actually detect them as a group. The hot gas will sit in the dark matter halo and get hot and emit X-rays. But you can't really, with X-ray telescopes, which are space-borne, very expensive, survey the whole sky to find, with deep images, to find X-rays. Something has to tell you where these things are, and this is the motivation of today's talk. And that is gravitational lensing. So this is what Professor Chitre was working on all through his life, and inspired so many people to work on. And in my own little way, I did my work inspired by Professor Chitre. And one of the things that gravitational lensing does, and if you attended Professor Narasimha's talk, you know all about this, so I'm not going to go through all of this, is that light bends, and light bends due to the mass on the way, and so the lens itself is in the foreground, a source is in the background, and the light bends around the foreground sources, and you can reconstruct the foreground, and it could be cluster of galaxies, group of galaxies, and you could reconstruct the mass distribution from the images that you see. What do you see? You can actually so the bending, the alpha, the angle that is done for individual stars is micro arcseconds. For individual galaxies, arcseconds very difficult to detect. So you need very high resolution images, and that's why the Hubble Space Telescope has been very useful. For clusters of galaxies, they are tens of arcseconds, and you can get nice features, which also you saw in Professor Narasimha's talk. But you need a certain surface density in order for this to happen, and essentially what you do is you take Fermat's principle and model this. It's you only need one result from GR, but the entire exercise is ray tracing following Fermat's principle. There are many ways of going from IUCAA to CBS, but light follows the optimal path along the geodesic, and you know that, and you can model it in simple geometrical way. And also, Sir Refzal in the 1960s actually pointed this out, and pointed out, of course, that it would be very useful in cosmology if such things could be found. And I happened to meet Professor Chitre at a time in Cambridge when the first discovery of these multiple image systems in gravitational lensing had just been made following Refzal's discovery in the early 80s by Bob Carswell and others at the Institute of Astronomy in Cambridge, where I was a student and Professor Chitre used to visit every year. What would happen is that if you have a lens and a source perfectly aligned, it would, as a result of this symmetry of the problem, give a perfect ring, called the Einstein ring, and this is about an arcsecond or so normally for galaxies, and sources at a cosmological distance, say about at a redshift of 1, and the optimal, it turns out that the optimal redshift at which a lens should be to do this is about 0.2 or 0.3. And so you get these lovely examples of these Einstein rings that have now been found with lots of, and so this is just this, the entire blue ring that you see is one galaxy, but it's just been distorted into a ring by the foreground galaxy, right? And actually what happens is that with the radio resolution, which also is about Sabak second with the VLA, you can find these Einstein rings. So these are examples of radio detected Einstein rings as well. So you actually detect them. So as I said, you need a certain critical density, and the critical density can come from not just the galaxy itself, but the surface density, the mass surface density can come from the group or the cluster. And this is why you can get a very complicated lens image, not just the Einstein ring, but it can tell you a lot about where the lens galaxy belongs. So if you look at, and so now people have been searching for these things, and Galaxy Zoo has a wonderful citizen science site where you can go and actually look through deep images from the SDSS or even from the CFH survey, etc., and the Subaru Deep Survey, and pick out if you can see these things. And you can see if you subtract the lens galaxy, you can look at the Einstein ring or multiply imaged strong lensed images. So one of the most important things that I'm talking about are these images, which are called quads. Quads are actually there are 5 images, multiple images, which essentially there's a misalignment between the source and the lens, and so the Einstein ring breaks up into 4 images. That's the idea, and you can see them. You don't see the 5th image because behind the galaxy. So the 4 images are in, and quads are, and this is, people realized at the very beginning of this game that quads, 4 image systems, of which we now know more than 100, very nicely characterized quad images, give you a lot of information about the lens itself. And you can see that if you look at these images, they are not perfectly placed symmetrically around the source, not all of them. And that is indicative of the geometry of the source and how much the system in which the galaxy belongs is playing a role in doing the lensing, right? And you can see what I'm getting at. I told you that it is very hard to detect groups at large distances, in fact, redshifts of 0.2 and 0.3, and this looks like it's a very promising system in which you can, if you look at the galaxy and you can mass model, make a model of the mass of the galaxy itself by looking at the multiple images that the Einstein ring has split into. And if it's very, very asymmetric, then you know that it's not just the galaxy that's doing the lensing, but there's something else there. And the something else will be the group to which the galaxy belongs, and it will be the mass of the group itself. And this group turns out to be a wonderful way of finding these groups at cosmological distance where you can't see them really from optical images or can't detect them directly. So this is, so you can see that complex images distort the caustics and cusps, which I didn't go into the great details of how the potential of the due to the gravitational potential due to the lens is described. But if you do mass modeling and if you put in extra ingredients, which are the nearby galaxies or the system to which the galaxy belongs, then you can find that the images, the geometry of the relative placement of the images tells you a lot about them. That's the idea. So here you are. There are various different kinds of features that come into this model, which a part of that Professor Narasimha talked about the other day. I'm not going to go into this is a whole course on gravitational lensing if you go into the fold asymmetry and the cusp asymmetry and things like that, but just shows you that if you look at the source plane and the image plane where the image is being formed for the lenses, then and what you see is that there are 4 images of a certain source which is being made by the galaxy, which is, you can see in the HST image, which is in the foreground, right? And then you say, why is this galaxy, which is nice and round and symmetric, giving you such an asymmetric pattern of the source of the images? And that is not just the misalignment between the lens and the path to the source, but it's also to do with the mass distribution, the clumpiness of the galaxy itself, and also the mass distribution and clumpiness of the surrounding system it belongs to, right? So you can see that by modeling the multiple images, you can figure out what the configuration of the mass distribution is, right? So here is here people started doing this 20 years ago, and Professor Narasimha here has done quite a lot of work with Professor Chitre on this kind of modeling of quartz. This is a wonderful idea, and so just looking at the asymmetry, you can figure out the mass distribution. And in very simple lenses also, you can get these are simulations that you can do to figure out where the images will appear and given the shape of the caustics and cusps, right? And then the very interesting thing is this term called external shear, which has been discussed long in gravitational lensing literature. The external shear determines the distortion of the symmetry of the placement of the images around the if you can see the centroid of the lens itself, right? And so if you do this mass modeling, it tells you where whether there is a group around, not just tells you the type of the source itself, the lens itself. The lens might not be a very smooth elliptical galaxy. It could be a spiral galaxy. It could have features and clumpiness within the lens itself, but it can tell you about the contribution of the surrounding system, which can be a cluster. In clusters, what happens due to the cluster lenses is that you get very elaborate systems of arcs and things like that, which other people have talked about. But if you're looking at just the distortion of the symmetry of the images, multiple images of say, a distant quasar, which is a source, by a galaxy that is at a redshift of 0.2 or 0.3, then this external shear tells you that there is maybe a small group there, which the galaxy belongs to. So here is an example. This is work I did long ago, and long discussions with Professor Chitre and also Professor Narasimha about this long time ago. So a very famous quad, B1422-231. There are 4 images. There's 1 here and 3 here, and the 4 images. And then Prashanjit Shah and Lilia Williams, my collaborators, contributed to building a model of this. And you can see it's very highly asymmetric, 3 on one side, 1 on the other. But the galaxy that you see in this HST NICMOS image, which is at a redshift of 0.3, the source turns out is very, very far away, redshift of 3.6, can be modeled. And if you model that, it predicts that there is a cluster, there is a small group there of maybe a velocity dispersion of about 400 kilometers per second. And that predicts it. But how do you see it? You don't see it. You don't see any of the other things around it. So we did wonderful reconstruction of the potential around it. Then I went through the X-ray archives, and in the ASCA, the Japanese X-ray satellite ASCA archives, we found, so for example, look at the difficulty of doing this kind of thing. This is 5 arc seconds by 5 arc seconds. High resolution, of course, HST is very high resolution, and then this ASCA image has a 45 arc minute resolution. This is a few degrees across. So if you want to find this group in X-rays, in the early days, it was very difficult, the Rosat ASCA era. It was very difficult to actually see this, but you can see that there is X-ray emission there, but it is hard to know whether it's associated with that particular galaxy that is the lens in this particular case. So I was involved in the building of a camera in Chandra, and so we got a lot of time as a result when Chandra, the high resolution imaging and spectroscopy observatory was launched in 1999. And after that, we managed to do quite a lot of imaging of these systems. And the first system that I proposed for was this, for example. And here is our Chandra image. And this is arc second resolution. not 45 arc minutes. This is arc second resolution, and the first one that we imaged. Here are the 4 images, and you can see a very large blob of X-ray emission sitting on top. This is the Chandra image the contours are from, and from that one could find that that's actually a cluster, a group which is of the temperature of the gas is about 2 keV, which corresponds to a very poor group, and so you can detect this group. So this is a group at redshift of 0.34, which you could never see in optical or radio observations, direct imaging of the galaxies themselves. And even if you saw the galaxies themselves, other than the central galaxy, which is this galaxy, of course, you wouldn't know that there is actually an association with the group there. But this gives you a feel for the dark matter halo of this particular group. So there are other quads that we followed up with external shear, and there are in the literature, not much work has been done on this since then. In the literature, there are some images of some of these groups that have been found in X-rays, and there's a very difficult thing to do in high resolution, very deep X-ray images can be used to follow up. But what you have to do is to model the asymmetry of the multiple images of the strong lensing system. That's just to show that in the Chandra X-ray image, this is the luminosity distribution in X-rays of the. It just shows very nicely the presence there. Here, other people have done similar pieces of work, 1608, 656. There, you can see how asymmetric these images are. There are the 4 images here. This is the galaxy in the middle, and the Chandra satellite actually picks up the emission from the group that this belongs to. It's a very efficient system of detecting groups. Now, as I said, there are about 100 quads, multiple image systems that are known. Out of them, maybe about 50 or 60 very well defined quadruple systems. And these quadruple systems have been used quite a lot in doing time delays and measuring the Hubble constant. There are 20 of them that have been monitored for a long time. I monitored 1422 with Alok Patnaik when he was at Jodrell Bank, for example, using the VLA. And you can find, and what is the time delay is that if you take the images, the multiple images, here are the multiple images, they represent images of that have a light travel time that are slightly different from each other, coming from the source to us. And so if the source varies, and it often varies in the radio quite a bit, in optical it's very difficult to find variations. If the source varies, then since their paths are very different, you would find that they vary at different times. Here's a good example of something that I've worked on quite a bit. This is the very first gravitational lens system to be discovered, multiple image 0957, the one that I said Bob Carswell and collaborators found. There are 2 images in that system. And if you look at the radio, the 6 centimeter, 4 centimeter VLA monitoring over many years, you can see that it varies, and the other, this is image A and then image B, varies a little later, and actually it happens to be about 422 days apart, the variation. And that tells you the exact geometry of the 2 paths. And this is what Resdahl had predicted and would give you a very nice measure of the Hubble constant. So quads are very important in this, and also in order to get cosmological parameters out of this, you have to model these lenses very well, and so you have to put in the group model the presence in the lens model, the presence of the group if there is one, in order to get out cosmological parameters out of it. So this is not just a way of detecting these groups, but also characterizing the cosmological significance of these lens systems. So quads are very, very interesting. Now, where do we go from here? I mean, there are very few quads known, as I said, about 40 or 50 quads known, and some of them are asymmetric, some of them have external shear, and people have tried to follow them up. But now, with the large surveys, a lot of these multiple systems potentially are being discovered. So this is a good time to go back to this, which was a very, very trendy thing to do 20 years ago. but due to lack of data, people didn't have much to follow up. Now strong lenses are being found in citizen science surveys. There are space warps that come from SDSS, or the Subaru Hyper Supreme Cam HSC Zoo. My colleague Anuprita More here has been doing a lot of this work. It's setting up citizen science surveys in which people are invited to just go on, any of you can go into these websites, and you are told how to look for these arcs and multiple image systems. And people have discovered quite a lot of gravitational lenses. School children have discovered gravitational lenses from these systems. There are no quads that have been discovered yet. The quadruple systems are actually very good for this kind of group finding. But these are examples of various arcs and gravitational arcs in clusters that have been found. And these can be followed up by finding the cluster. So here are, and this is one example I showed you from the Canada, France, Hawaii telescope survey.
An interruption, about 4 minutes. Okay?
Yes, I'm done, almost done. Thank you. So, so for example, these are various big surveys that are either done with the CFHT or with Subaru. Both are in Hawaii, where the actual optical images can be obtained with 0.2, 0.3 arc-second resolution. That is where you can actually get image quality in a large telescope, 8 to 10 meter class telescope, where you can find these multiple image systems where the separation between them, as I said, is less than an arc-second. And so this is now being done, and people are going through all these images, trying to figure out, and they're very difficult to detect because there are all kinds of imposters. There are actually 4 images, and you would, unless you take the redshift of them, you wouldn't know whether they are of the same object or not. They could be 4 independent galaxies, right? And so you have a lot of follow-up to do before you can identify something as a quad or a multiple image. Even there are images that where you have 6 or 8 images systems. They're very, very rare, but the more the better, because then you get independent measures of the independent parameters that can be constrained in the models themselves. And this is another example, very recently, Anuprita's work from the Hyper Supreme Cam. You can see lots and lots of these candidates have emerged where there are some are arcs and some of them are multiple images, and they're being followed up to figure out whether these are genuine multiple images or not. And once we have a very large, hundreds of them, a large sample of these multiply imaged quasars, group scale mass distributions can be found around the lenses. And this will lead us in the next generation of these images by following up with say, X-ray telescopes to figure out whether you can find groups at cosmological distances. And this is where the fun lies in figuring out the environments in which galaxies live at higher redshift. We've studied galaxies living in groups and clusters at very low redshift, but if you want to go higher and higher redshifts, you have to detect these things, and gravitational lensing provides a very interesting way of doing this. I'll stop there. Thank you very much.
Very kind of you. Now, there are 2 questions I see. The first question is, could the quad images be used to detect the presence of gravitational waves by observing the distortion in them? The question is from Rohit Sharma.
Gravitational, how gravitational waves interact with gravitational lensing is being worked on. I mean, there are many people I know who are working with gravitational lensing of gravitational waves. Our measurement of the various parameters of gravitational waves is very much in its infancy right now. We've detected gravitational waves, but actually imaging the sources themselves and corresponding to gravitational waves and detection, it takes a long time. Currently, we have detected gravitational waves from mergers of black holes and stuff like that. And certainly these gravitational waves that come to us are lensed by, can be lensed, strongly lensed. Whether we will see strong lensing effects in them is a very interesting question. It's only that kind of work is only starting now. So it would be very interesting to ask this question a few years later when people have done this kind of work. I know of many groups who are trying to actually work out whether there are observable effects to find gravitational waves.
Thank you. There are two more questions, of which one I am going to skip because the person wants to be explained again. I request that person to talk to you independently. So I go to the final question of the session. Could you elaborate on cold dark matter density being measured using gravitational lensing? The question is from Ibrahim Mirza.
Yeah, so I told you that essentially all these various source models that are made, right? And I don't know which one to, so what happens is that you are looking at a galaxy. I can look at this galaxy, for example, and you can image the galaxy itself, and that's the lens. Remember, this galaxy is at a redshift of 0.2 or 0.3, which is in the foreground, and the source is very much in the background, and that's at a redshift of 1, 2, 3, something like that. Okay, and so you have a system in which you can measure, you can build a model of this of this lens in the foreground, and what you're measuring is the total mass in the galaxy, not what you're seeing in light. So it is the matter, and it's cold dark matter, of course, because dark matter is cold. But then you're measuring the effect of the total matter, and in systems where the galaxy belongs to a larger system, which means that there is a group or a cluster around it, as long as the critical density, the surface density mass per unit area around the galaxy, that is above this certain critical density, then it will have an effect on the lensing, and so you can up to a distance from the center of the lens up to which you can detect the effect of the lensing in systems like this. Then you can actually quantify the distribution of dark matter out to there, and it's often out to where the Einstein ring is, or slightly beyond. And so you can for a limited place, you can actually find whether there is a lot of dark matter there, and sometimes you can measure only the dark matter halo of the galaxy itself, which is the lens, and sometimes you can even extend that model out to what I call external shear, which means the effect of the dark matter distribution of the group or the cluster itself, right? So that's it. What you're doing is, because in such systems, dark matter is the predominant component of matter, and you're measuring the full matter, all the matter. That is, when the gravitational lensing happens, you're not distinguishing between baryonic matter and dark matter, or the stars and the dark matter. You're seeing the effect due to all the matter. And so if you can figure out how much baryonic matter there is by measuring the light and measuring the X-rays, etc., from it, then you can subtract it from the total matter estimated from the lens exercise and find out how much that matter is.
Thank you, sir. Shall we now move on to the next speaker?
Of course, thank you. I'm going to stop share, and thank you very much.
Thank you.
While the changeover is taking place, let me introduce the next speaker, Amit Seta. As I said in the beginning, it's a charming moment for me to introduce a former student of CEBS, in a way mine too, in a conference participated by international luminaries and Nobel laureate. Amit is from third batch of CEBS, which was one of our favorite batches, as there were many bright students. He was in competition for top honors with at least 3 more people. Aklan Bomik, I think you will hear him in the next session, Saranyo, and Angana Mandal. I do not know who won at the end of the course. Before I invite him, I want to share one charming moment, which I consider as an honor. Professor Chitre used to peep into the laboratory and pull me out for some discussion, consultation, biting my ear. At one occasion, Amit said, "Sir, don't pull out Professor Nagarajan." I felt I am valuable and felt honored. I cherish it till today. I don't know whether Amit remembers it. Amit is a rising star, so he will shine on his own. So I don't want to say anything more about him. I would rather like to have more time for his talk. Please, Amit, carry on. He is in from Australian National University, right?
Yeah.
Okay.
Thank you, sir. Thanks a lot for this kind introduction and for remembering me and my time at CBS. First of all, just to confirm, can everybody see the full screen and hear me well?
Yes.
Yeah, thank you. So, hello everyone. First of all, I would like to thank organizers for giving me this opportunity. And it's an absolute pleasure to see all of you and talk to all of you. I think that itself is quite nice. And I'm very happy to tell you a bit about what I have been doing since I moved. I was a student at CBS from 2009 to 14. Then I did my PhD from Newcastle University, and now I'm postdoctoral fellow at the ANU. And today I'm going to talk about magnetic fields in the Milky Way, specifically from pulsar observations. And this work is done with Christoph Federer here. So, yeah. So first, okay, is slide changing fine?
Yes, perfectly fine.
Yeah. So first of all, I pay my tributes and respect to Professor Chitre. He taught me 2 courses, astrophysics and fluid dynamics. I distinctively remember his teaching style. And whenever we had some question, we used to go to him, and he would always give very helpful reply. That was and will be very, very calm and very helpful in his replies. So he helped me in various ways, some of which I don't even know, I should say that way. I last met him in summer of 2019. We have been in email contact after I left CBS, but I last personally met him with few of my other friends at Cambridge when he was visiting with ma'am. And we had a very long chat about various things. And it was clear to me that as I progressed in my career, his suggestions changed accordingly to make sure they are helpful to me. So last time when I met him, we also had interaction about not just professional life, but also personal life and long-term goals and short-term goals and various things. And it was very interesting to see him having a lot of inputs and very helpful inputs in various ways. So I think it is an honor for me to talk here in a symposium which is in his memory. In hindsight, I also thank him for establishing CBS, because this is the place where I met a lot of excellent teachers and friends, lot of whom I'm still in touch with, and many of these people are in the audience. So it's an excellent and quite nice for me to see you all, talk to you all. I pay my respects to Professor Chitre's memory. I will always remember him as a very calm and helpful person, and very detailed. The detail with which he explained me astrophysics, the same detail was there when he gave me suggestion about my career or about my personal life and how things change with time and returning to India and everything, such like things like that. So it always very detailed. So that was helpful. And thank you all again. Now moving on, I would like to talk about magnetic fields in galaxies, in particular the Milky Way. So to give you a brief introduction, the interstellar medium of galaxy, written as ISM here, is basically stuff between stars. But I don't think the term justifies how much dynamic it is. So this stuff between stars has a lot of components. It is permeated by thermal gas, cosmic rays, which are relativistic particles. magnetic fields and dust. And it's very dynamic system because there are continuous supernova explosion going on. And this supernova explosions stirs this medium and generates turbulence. It's very much like stirring coffee in a cup. That's the usual analogy given. And the driving scale of turbulence, which you can think of as size of the cup or the length scale at which you are turning your spoon. So that turns out to be 100 parsec. 1 parsec is 3 into 10 to the power 18 centimeters. So it's around 100 parsec, and this amplifies magnetic fields. This is a very interesting idea called dynamo theory. So basically there is turbulence which amplifies magnetic field, and this magnetic field is traced by a lot of tracers, some Faraday rotation, synchrotron emission, different kind of polarizations. But what I'll be talking to you today about mostly about using pulsars to look at this magnetic field. To give you an estimate of strength of this magnetic field, it is around 5 to 10 microgauss in the Milky Way and nearby spiral galaxies. And the energy density of these various components I was talking about, the stuff between the star, are comparable. So all of these components are important to consider the dynamics of this interstellar medium. And one question we usually ask is, why study galactic magnetic fields? I would like to say it is an interesting quantity in itself, but also it is involved in a lot of other processes. So it's important to understand the strength and structure of magnetic field. And for this talk, I just focus on pulsars. So strength is around 5 to 10 microgauss, but what do I mean by structure? So this is a very nice image taken from the Planck work. So basically what you are seeing is this draping things which you are seeing is basically roughly is a proxy for, I would probably say, the magnetic field direction. So you can see it's not just, so magnetic field in spiral galaxy is not just a spiral. That's what I'm trying to convey here. It's very rich in structures. There are these loops going around. You see towards the edge, there is some flaring. So it's very rich in structure. And there are, again, this is a dust polarization map. This obtained from dust polarization. There are various ways to probe it. This image is particularly nice because it is like art and science mixed together. So I usually show it. It's, I think, motivated by Van Gogh, and I think some French astronomers were involved. But to go ahead, so this is the Milky Way picture. It is 5 to 10 microgauss, rough approximation. The next thing which I will be talking about is pulsars. So pulsars are rotating magnetized neutron stars in the Milky Way. So it's like this. It has this light cone kind of emission, and when it comes towards us, you will see a pulse. And if the next direction comes towards us, because it's rotating, you see this pulse. So they are identified this way, and a lot of them are observed in the Milky Way, and it's a field in itself, pulsar astronomy, where pulsars are used for various things. But what I'm interested today is to use pulsar to estimate Milky Way magnetic fields. So if there are such observations available with some other kinds of observation, multiple frequencies, one can estimate something called as rotation measure and dispersion measure. So these two quantities are basically observed quantities. So they can be derived from observations. But these two quantities are also related to physical properties of the medium between us and the pulsar. So rotation measure depends on the thermal electron density and magnetic field integrated along the whole line of sight, because pulsar is at some distance from us. And then the dispersion measure depends on the thermal electron density, again integrated along the whole line of sight. So mathematically, you can think that there are two quantities. One depends on NE and B, another depends on NE. If you divide one by the other, you will get some idea of the average magnetic field. Now, this is average along the line of sight because the quantities are both integrated. So the RM and DM, which I'll use the same short forms throughout the talk, are rotation and dispersion measure obtained completely observationally from the observational data. could be related back to the physical properties of the medium between pulsar and us to give us this average magnetic field. I have just shown a cartoon here showing the same thing. So suppose if there's a pulsar here at some distance, this observer basically means a telescope, and there's an interstellar medium between us. Based on the signal you get from pulsars, you can derive rotation measure and dispersion measure, and then can divide one by the other to get some estimate of average magnetic field. Now, this was this is known from long time back. The first paper which kind of described this was Smith 1968. To give you an idea, pulsars were discovered in 1967. So people were very quick in trying to use them to estimate magnetic fields. And the idea was first put forward here. And in 74 itself, there were few observations of pulsars. So each of this circle you see is basically a pulsar observation. The sun is 8 kiloparsecs from the center, so we are somewhere here, and you're observing various kinds of pulsar everywhere. So basically each line of sight you go from sun to the pulsar, you can probe magnetic field average along this line. Then if you see this pulsar, you have again rotation measure, dispersion measure from observations. You can measure pulsar properties along this line. And there are many papers. It's just the one paper I put in, but then there are series of papers in past 50 years who have looked at this into much detail, and the data is much richer now and is much accurate. So the first question is, what am I doing? What is my motivation? So people have been using this technique for 50 years, and there was also this discussion around, I should say. So the basic idea, just to repeat again, is there is an observed rotation measure, observed dispersion measure. You divide one by other to get the average magnetic field. Now, mathematically, you could see that if these two are correlated, this method won't give a right answer because they will be enhanced locally when these two are correlated. So this estimate assumes that NE and B are independent. And in this talk, I'm trying to understand the effect of if they are not independent, then how will it affect this estimate? So pulsar observations gives RM and DM. You use them to estimate magnetic field, but on the way you assume that the thermal electron density and magnetic field are independent. And if it is independent, how does this estimate affect it? The first question to worry about is, where do you expect such a correlation? Like, where do you expect this to be correlated? One of the places you can think of is compression. So suppose if there's a parcel of gas with some thermal electrons and magnetic field, if you compress it, it will now occupy a smaller volume, and both of them will go up because this is the number density, and magnetic field also gets enhanced. So the regions where the compression is high, NE and B will be correlated. And we know there are many such regions because supernova explosion drives turbulence and there are shocks around. So the basic expectation is there are these regions where both NE and B goes up. So RM and DM will both go up, right, based on this formula. And this will go up in a correlated way. And the basic question I'm trying to ask is, how does this correlation between thermal electrons and magnetic field affect this interpretation? So the first hint to this idea is looking at observations actually. So these are all observations with the rotation measure, mod of rotation measure, because the rotation measure can be negative. B can point in a different direction, is correlated with DM. So RM and DM are correlated over large sample. There is some scatter, but this is completely observation. So there is some hint that such an idea is probably there. It can also happen due to other reasons, but it's good enough motivation to go and look for this effects of this correlation. So what we do first is to look at this in a controlled way, in a controlled setup. The basic idea is to solve, is to drive turbulence numerically. So this is using numerical simulations. I'm showing some equation, but don't worry too much about it. It just looks maybe a bit more complicated, but the basic idea is numerically drive turbulence. And the compressibility can be changed by using with different Mach numbers. So you numerically drive turbulence in a box, you have thermal gas, you have magnetic fields. When Mach number is high, or when the compressibility is high, you would expect this formula to give you incorrect results because of this analogy, because of this small cartoon picture, and how wrong it can go. That is in a numerical setup. So what I'm showing here is there is some results from numerical simulations. This is the thermal electron density for low Mach numbers, the two top panel, and this is the magnetic field strength. For higher Mach numbers, Mach number of 10, this is the thermal electron density and this is the magnetic field. So you can see here, if you look at this region, the thermal electron density is higher, even the magnetic field is high. So there are such correlations at higher Mach number. Of course, there is no such correlation at very low Mach number. So this is just a parameter to control compressibility, because we'd know where there is in compressible medium, such cases would come up, and this could affect the estimate. So these are just some pictures I'm showing, but the basic interest is now from simulations. I calculate both the magnetic field strength because I know it's a controlled way, and what is this Rm by dm. This factor is just some normalization, 1.23 to Rm by dm, and I'm showing here 4 plots for Mach number 0.1, 2, 5, and 10. And what I'm showing is the probability distribution function of both these quantities from the simulation. So basically, high probability means they are very probable in the domain, and then the probability decays as it goes to higher and higher values of magnetic field estimate. The dashed line, the black dashed line is a Gaussian fit. So to see how Gaussian this is, the solid line is the synthetic observation, observational result, and the dashed line is what is the actual estimate in simulation. So as you can see, the dashed line and the solid line are not very far away for low Mach numbers. But for high Mach numbers, there is a lot of difference. So basically, this equality holds good for low Mach numbers or moderately low, not very compressible medium, but in a very compressible case, the estimate can be wrong. To get a better idea of how wrong it can be, again, this is all simulation, so it's controllable. What I'm showing here is a 2D probability distribution function of those two quantities. And for low Mach number, the match is very good. If you increase the Mach number, the spread increases a bit, but on an average, things match. But at higher Mach numbers, what you can see in the background color is from simulation. The blue line is our expectation, and the red line is the best fit to the data. As you can see, the match is very good here. It is okay here. Here, certainly the magnetic field estimates are wrong by a factor of 2. And at higher Mach number, which is 10, it can go away by a factor of 3. So for very high Mach number, the difference can be as high as factor of 3. Now, this is an observational result. We did a guess that in compressible regions, this would be a problem. We did a small simulation in a controlled way where we saw that, yes, it is a problem and it can go wrong as by a factor of 3 or so. Now, coming back to observations, because this was, I think, Professor.
Yeah, about 2 or 3 minutes. Can you speed up?
Yeah, I'm done. So if you look at
If you don't want questions, you can take more time.
No, yeah, I'm done. I'm almost close. Okay. So this is the observational PDF. Now, what I was showing initially is the theoretical, is the simulated one. This is the observational PDF of the same quantity. Of course, we don't know the magnetic field here, because if you would have known, this all is not required. This is the observational PDF, and it is very good Gaussian. So the first conclusion is probably the interstellar medium on large scale is not supersonic, because these are data at very large scales. And the small scale field strength is around 0.5 microgauss. You can estimate it from the standard deviation of this curve. So these are the two results which we get immediately from here. The next idea is to try to look at independent observation of any. I mean, we were taking a product till now to calculate Rm, but an independent observation of any is H alpha data. And if so, IH alpha is related to any square. So if any is correlated to B, then 1.232 Rm by dm will be related to the intensity of H alpha. But we don't find any such correlation. These are like 1,000 pulsars. There is a lot of scatter because this can be due to systematics or the errors in Rm and dm, but there is no such correlation found. So the basic conclusion is on kiloparsec scale, NE and B are not correlated, so the formula is fine. Or these correlated structures occupy only small volume. So to sum up, I would say that this relation, which has been used from 40 years long, 50 years long for the estimate, is probably fine. It depends on Mach number, so could be a problem at smaller scales, but for kiloparsec scale, it's certainly fine. The ISM is not supersonic. At kiloparsec scale, the magnetic field strength is around 1.1 to 2 microgauss. And with other independent measures of thermal electron density, there was no correlation. So probably at this formula gives perfectly fine answers on kiloparsec scale. This might, however, break down at sub-kiloparsec scale. This is just a next additional point that one must also worry about such things while calculating magnetic field from fast radio burst, which are almost like extragalactic pulsars. Whatever I've covered now with all numbers and much more detail is in this paper earlier this year. And I'm happy to take questions now or via any email. Thank you.
Thanks, Amit, for cutting short your talk. There's one question from one of our students, Pratyush. Why is the ratio of rotation and dispersion measure giving us magnetic fields? Could you give a physical intuition?
So if I go back to here, so this, we know this quantity is related to NEB integral, and we know this quantity is related to NE integral. So you know two quantities in an integrated way, like the integral is known from observations. The left-hand side of both of this equation is completely from observations. It's just more of a mathematical trick, I would say, to extract B, because that's what we are more interested, that's what people are more interested in generally. It's difficult to get a good estimate of B. So they just divide this by this, and this 1.8 is just inverse of this guy to get an average. Whatever you get is an average value because it's again from an integrated thing. So it's just, you are given two integrated values and you want to get some information about the integrand. So you do this. It's more of a mathematical thing.
Thank you. Now, Sankit has an interesting, nice, simple question. How are faint magnetic fields in faraway space object measured or estimated?
Yeah, that's a very interesting question. So these pulsars are mostly observed in our Milky Way. There are few in large and small Magellanic Cloud, which are close by irregular galaxies. So in far away, there are some, in very far away from us, there are some other methods. These pulsars methods won't work because these guys are only detected in the Milky Way and some in irregular galaxies. So in very far away galaxies, you can still measure rotation measure, but then you have to come up with some model or some other observation for NE to calculate the magnetic field strength in some far away galaxy.
Thank you. I think we are running behind schedule. I'm not a good chairman.
Actually, Professor Nagarajan, there is a hand being raised by Professor Avinash Deshpande. So maybe we can request him to unmute and ask his question very fast.
Okay.
That's okay.
Please go ahead.
Okay. Yeah, thanks. I have one comment and one suggestion.
Yes,
the comment is related to the distinction between the change in DM versus change in RM when you gave this simple example of a same cloud compressed along the line of sight. You will find that the DM does not change in that example. The RM does change and the ratio will. Okay.
Agree.
The suggestion is that since you are looking for clumping and situations like this, you will find the scattering measure, the data on pulse scattering in the directions of interest would actually give you a separate handle on certain other dependence on the electron density. In fact, electron density fluctuation, which is exactly what you're looking for. You might find it rewarding to have a look at it.
Yeah, okay. Thanks a lot. Thank you. I never thought it that way, frankly. Thanks a lot.
So shall we move on to the next speaker? while we make the transition, let me say a few words about Rohit Sharma. Another charming moment for me. Can you hear me? Am I audible?
Yes.
Yeah.
Yes.
Welcome, Rohit. You are from the very first batch and one of the first persons whom I knew by name. The reason is you have the same name as the cricket current vice captain Rohit Sharma. He burst on the scene at the same time as you joined CBS. So you are always in my memory. The other thing I fondly remember is discussing with you your careers and so on midway through the MSc program. If I'm not mistaken, you are from the DA family from Indore. You can correct me if I'm wrong. I'm very happy that from the small beginnings, you have also risen to status of a rising star with Amit and Aklant. I think you will know make a galaxy for CBS. I find that you are in data science center. I do not know what is the data that is handling, which I hope to see or hear from your talk.
Sure.
Can we just move on to Rohit now so that he gets more time? We are running behind schedule. 15 minutes, okay for you?
Yes, I will take. I will cut my talk if needed. Yeah.
Depending on, I said, if you don't want to take questions, you can do. Only one small request. I am committed for another meeting. Very, very strange coincidence. So I may leave about 2:15, 2:20. The coordinator, whoever is taking care on the control center, might do the finishing touch. Okay.
Yeah. Okay.
Thank you.
So quickly, you can see my screen and changing of slides, I guess.
You are not presenting yet.
I'm not presenting currently.
I think he disconnected. Yes. We cannot see you or hear you. Can you unmute yourself?
Yeah. Now is it fine?
Yes, everything's fine.
Okay. Yeah. Thanks a lot. Thanks, Nagarajan sir. Yeah. So my name is Rohit Sharma, and I'm currently a postdoc at University of Applied Sciences and Arts, Northwestern Switzerland. And it's my privilege to be presenting this talk on solar radio physics. Although this is a sad occasion for us. I come from the first batch, which started in 2007 and graduated in 2012. And coming from the first batch actually made us close to Professor Chitre. So these are so few memorial pictures which I am presenting, and this is the first picture which we had our batch and other dignitaries, and this was the first CBS cake which we cut in 2008 after 1 year. And yeah, Professor Mathur and Professor Husur are also there in some of the pictures. So people have been talking about Professor Chitre and his personality and his personal traits. I will not repeat it, but I will just say that as we entered CBS in 2007, there was no building, nothing. He actually made us CBS a second home, and he ensured that we feel that way. And he actually gave his own. He went out of his league and gave us a personal touch, and we are one of the fortunate enough to have that. And the many times when he actually invited us to his home, to various restaurants, and just chat on a friendly level. And we just used to just hear him about his days in Cambridge, and his words of wisdom, and we truly remember that. The last encounter which I had with Professor Chitre was in NCRA, where I was doing my PhD. And that was in MW Sky Conference. That was also for felicitating Dr. Govind Sarup, another pioneer. At that time, yeah, so I met Professor Chitre, and we were discussing about the work, my work. So yeah, so it is a huge loss for us, and we truly lost a fatherly figure in him. So in that memory, I will I will motivate solar sciences using his favorite analogy, which is Rosetta Stone. Just like Rosetta Stone opened new horizons in linguistic sciences and historical sciences, solar physics is doing same for the stellar physics and plasma physics in general. So I will not go into the details of the basics, but there are a few things which I want to highlight in the solar structure. One is basically the problems associated with the solar atmosphere. So as we know that sun has a photosphere, chromosphere, and corona as three layers of the solar atmosphere. And the corona is connected to interplanetary medium and which directly impacts us. So we need to understand from the space weather point of view all these three regions, and we know that they are all driven by magnetic fields which are produced inside the sun, and then they protrude out. There are two interesting problems which have been there for some time now. One is the coronal heating problem, which looking from outside defies the second law of thermodynamics, which is basically why the corona is a million degree hotter and sitting on top of a cooler chromosphere. And the second problem is basically the particle acceleration problem. So if you look at the solar wind profile, the velocities are pretty high, and they tend to have a longitudinal profile. So the fast solar wind comes from the northern and the southern regions near the poles, while the slower solar wind comes from the equator. So how does the particle get accelerated here in these regions, and what is the fundamental mechanisms which is accelerating these particles in the corona? So these are some outstanding problems which we try to understand in this using the new instruments that we will discuss. So, so in this regard, so firstly, this coronal heating problem. So uh, one of the most plausible theories to explain coronal heating problem is the nanoflare theory, which says that there are these multiple flares which are occurring all over the sun at different times, and then they heat up the ambient corona, and then so therefore you have a hot corona. And what is the mechanism by which these flare occurs is a subject of research. So here I'm giving you two examples where on the left you see a typical solar flare profile, solar flare image, which is basically a huge amount of energy is being released in a smaller time, and this energy which is being released is being distributed in radiation and hitting the ambient plasma, and also doing some particle acceleration. If the in some of the cases under certain conditions, when the plasma around is quite dense and the eruption is quite violent, then you can have something called coronal mass ejection, which is where the material is being pushed out of the corona into the interplanetary medium, and we should pray that we do not go close to coronal mass ejection. Otherwise, it's a huge mixture of shock waves and high energetic particles, which will just evaporate you. So these are very dangerous phenomena in the space weather, and the fundamental mechanism which govern these are the magnetic reconnection processes. So it hugely depends on the local magnetic field topology, but overall we can differentiate it in two ways. One is basically you have a magnetic diffusion magnetic reconnection which is happening in one solar loop. So oppositely magnetic field lines, they come and diffuse, and then from this region the particle get accelerated upwards and downwards. The particles which get downwards, they tend to emit gyrosynchrotron emission, while the particles which go upward, they tend to emit radio waves. And when the particles actually go down and then they hit the dense chromosphere, then they also emit hard X-ray signatures. So in a way, X-rays and radio are sort of like complementary signatures of radiation from the same reconnection event which is happening. This can change. This can also happen when you have a different loop structure. As for example, shown here, you have neighboring magnetic field lines, which is oppositely charged as compared to this loop, and then you get a diffusion region here. So these are the scenarios in which you can get particle acceleration and heating at the same time, and could be responsible for the heating of corona. So what is so special about radio emission in such? So radio emission actually comes from a diverse range of plasma. So on the left hand side, I'm showing you an image of basically image of white sun at different frequencies, and if you see at higher frequency, you recover the photospheric structures. So the optical depth, so the optically the radio emissions are thin, but as you go to the higher frequencies, the height at which the radiation become optically thick is actually is decreasing. So you can actually tune your frequency to sample the height at which you want to look at the coronal plasma. In addition, the plasma emission mechanism for the burst actually it changes as you go from high frequency to low frequency. So at high frequency, you get mostly gyrosynchrotron gyro resonance emission, because there the magnetic fields are quite high. It's quite close to the coronal. It's quite close to the chromosphere. While if you go to the low frequency, you go high. You are going higher up in the coronal height, and the plasma emission mechanism and the Bremsstrahlung emission mechanisms become dominant. So this is something to keep in mind. So we did a couple of studies where we tried to look at high frequency radio burst in conjunction with X-ray radio burst. So this is an example of the radio burst happening at high frequencies. By high frequency, I mean in element about 1 to 2 gigahertz in that frequency range. So in this frequency range, so in this event, we see 6 spikes. So these spikes are actually coming from electrons gyrating along magnetic field lines. So these are the sort of like signatures of particle acceleration. And these actually they were co-temporal with X-rays. However, when we image them, then we find that although they are co-temporal, but they were not co-spatial. And further analysis of basically by fitting gyrosynchrotron emission fits, we can get a handle on the coronal parameter which are involved there. So that actually says that we actually find that the populations from X-rays and radio, they actually were not matching in this particular event, and subsequently other events also. So there must be basically they must be coming from two different loops, or they must be two different populations of electrons which are there. So that just highlights the complexity which is involved in the particle acceleration picture in this regard. And also there is asymmetry in their location. So in this there is this northern ribbon and southern ribbon, but we find only radio particle acceleration in the northern ribbon. So it is highly governed by the magnetic topology in this. Also, when we look at the flux density of the flares and the quiet sun, we find what we find is basically there is a huge difference in the flux density. So, for example, if you look at this dashed line and these colored curves, they represent the burst and this represents the quiet sun. So if you go to the low frequency, then the contrast between burst component and the quiet sun component becomes quite high, and this actually allows us to detect faint features in this frequency range. So if you want to look for faint features, for example, like to investigate the nanoflare picture, and because nanoflares would give faint components, we would have to go to the low frequency side rather than the high frequency side. So um, in the low frequency side, there were not many telescopes till now. There were telescopes, but the main problem of those telescopes were that for observing the solar observation is that the solar observations are quite dynamic, so they change in the order of seconds. And you really and those telescopes use interferometer, typically use synthesis imaging, which actually average out these features because their integration time was like hours. So you cannot really detect these faint sources on the sun. But with the new generation interferometer like LOFAR and MWA, you can actually do snapshot imaging and try to go and detect the low frequency side of the flux densities and try to see the weakest features in the low frequency radio. So for my PhD, I used Murchison-Whitefield array, the data from Murchison-Whitefield array, the solar data, and why we used, because it is very sensitive instrument. It really has a very dense core, and it is also located in RFI free environment. So this is located in Western Australia near Murchison, where the human population is like 10 milli humans per square kilometer. So nobody actually lives there. So it is a very good RFI environment, and it's very good for doing radio astronomy. And here is an aerial shot of that interferometer, and each of these one is tiles. So one of the why is the MWA is important for solar observation? Because it has a few advantages. The main advantage is that it has a dense core. If you look at this is a layout. The black dots are the layouts for the phase one, and it has a very dense core. So it has lots of small baselines, which gives lots of Fourier components, and which in turn results in high sensitivity. So that is a key feature here of MWA, which we exploit to find the faintest features detected in meter waves. So in this, using this capability, we can actually image sun at 0.5 second resolution, and here is an example of that. There is one problem which I worked on, is the flux calibration problem for radio sun. Typically, how do you do the flux calibration? Is basically you look at the calibrator, and then you look at the sun, and then you basically compute what would be the appropriate flux. But for observation of sun, actually you need to have the attenuator, and if you apply the same attenuator for the calibrator source, then you would see nothing. So basically, we devised a new a pipeline based on the cross correlation and baseline based approach, and using this we could actually make a very good flux calibration. And here is the result from the flux calibration as a function of the frequency range. And using this, we could actually able to find very faint features. So these faint features were like 2 orders of magnitude, which the 2 orders of magnitude less than what have been reported till now by various in the literature. And these features were quite numerous, and the frequency and time suggests that these are like 4 to 5 megahertz in bandwidth, and 1 to 2 megahertz in time. So that is an average statistic of these features, and these would be in the range of microflare to nanoflare range in terms of the energies. In this, I have now also devised a technique where, based on the visibilities, and in using this technique, actually we could find even go deeper, and we could detect the brightness of like 10,000 Kelvin, and we can actually image them and associate them on the solar image. And most of them actually you see here is associated with the active regions, and some of them are actually not. So those are also very interesting. So this is basically the faintest features that we are detecting. This work I'm currently writing it. These so I think I'm short on time, so I will actually just briefly say that we have also done it. So when the radio waves actually propagate, they suffer the propagation effects. For example, refraction and scattering. And when they do that, these occur because of the kilometer to tens of kilometers to thousands of kilometers of density inhomogeneity which is present in them. There is a simulation which actually illustrates this very nicely. So there's a photon packet which is being released, and then because of the density inhomogeneity here, it just disperses as it travels. So using quite some radio maps and basically building a model of thermal brainstorming, we can actually get a handle on how much these density could be, so that it give rise to such fluctuations in the maps, for example. So these are the model maps, and you can see the differences in observed maps. So in this, using this technique, we could identify that the delta n by n, where n is basically the electron density in the ambient corona, should be of the order of like 1 to 5%, and the H should be of the order of 40 to 100 kilometers. So we can use these sensitive images to actually say a lot of things about coronal plasma, and these would actually increase our understanding of how does corona is structured, and how does the propagation take place, and how does the particle acceleration can also take place. So this one slide I want to share for the students of CBS, and so for the future missions, actually there is a mission. The largest mission is basically the square kilometer array, which the square kilometer is basically the effective area of the telescope, and this will actually decrease. This will actually increase the sensitivity limit to two orders of magnitude what we have with MWA. So this would even produce lots of data, and there's a lot of science which is being hidden in these, which will be presented in the data of SK, which will share. And the second point I wanted to make is this data, and in conjunction with the other instruments which are space-based observatories like Solar Orbiter and Fargo Solar Probe. So these instruments actually are in situ instrument, and it actually provides the data of various properties along the as it travels along the interplanetary medium, and also some of the imaging characteristics. For example, the Solar Orbiter recently discovered this campfire-like features in UV, and so this, along with, in conjunction with the radio observations, will provide a lot of unraveling of various science questions that are currently present. So it is a very good time to get into all these missions, because then you will get the handle of the data, and then you can study lots of science problems using these. So, and we also have a Indian mission on Aditya, which will be located in the L1 point, and it also has various instruments, including various spectrometers, spectropolarimeters, and also in situ instruments for measuring particle energies. And so basically, a conjunction of all these instruments will actually help us in understanding particle acceleration and other coronal heating, for example. So at the end, I will just summarize. Yeah, so it's a good time to get into solar radio physics, and with the new observations, with the new instruments, we are getting new observation constraints, and this is sort of like a revival of solar radio physics, which have been dormant from past 2 decades. So I will stop here.
So thank you, Rohit, for that scintillating talk. And Professor Nagarajan had to leave because he had another commitment at another meeting. So let me ask you the question. So since we are already delayed quite a bit, maybe we can go for only one question. So the question is, since the structure of coronal observations occur at small scales, how do we deal with ambiguities and misleads, even with fast devices? So this question is by Anand.
So I agree that there is lot of ambiguity. So that is where we have to be very careful. We have to isolate the event, or the event selection such be that you basically resolve out this ambiguity. So and that can happen when you have observations from multiple perspectives, including the wavelengths. So if we have if we have observations from various perspectives, then we can probably build a coherent model to remove these ambiguities.
Okay. Thank you, Rohit. So with this, let me thank again all the speakers of this session for giving such wonderful talks. And so we will take a break of 10 minutes now, and the next session will start at 2:30. So thank you once again.
Yeah, I just want to say that if you have any questions for any of the speakers, please keep sending them to question box,